Hi students, welcome to my lectures on chemical reaction engineering. In our last class, we have discussed about the design equation for the batch reactor and we have solved one problem using the equation, that is finding the time for the required conversion. Okay. In today's class, we are going to discuss about the graphical solution to design a batch reactor. Yes, in the last class we have solved an equation and analytically we have found the time for the given conversion. In today's lecture, let us go to the graphical solution. Imagine I have the batch reactor of capacity 2 liters, and you know that in the last class we can able to calculate the time based on moles, 2 based on concentration, 3 based on conversion. In the today's lecture, we are going to find the time using 1 with moles, 2 with concentrations using a graphical method. On this hand side, I have given the graphical method based on moles. On this side, I have given graphical solution based on the concentration. It is simple. That means you do not know about the order of the equation. Okay. In such cases, what you are supposed to do, because if you do not know the order, you cannot plug whether it is K or KCA in the design equation and solve for the time. Here you do not need to worry about the what order reaction that is happening in the reactor. And if you know the experimental data, from the experimental data you can able to find out time for the necessary conversion. Okay. If you remember this equation, time t equal to integral Na to Na0 dNA by minus Ra into V. Okay. And you do not know what order, so you cannot make minus Ra equal to K or KCA and integrate the equation, you cannot do that. And instead of that, we have to plot one variable on y axis, another variable on x axis, plot the experimental data. Through the experimental data, find out the area under the curve. From the area under the curve, you can able to calculate the time. So, I mean here Na to Na0 1 by minus Ra into V into dNA. You can see it is a kind of integral y into dx. What is y and what is x? What y, see you can compare y into dx. Y is nothing but 1 by minus Ra into V, right, and x is nothing but Na, right. That means integral y dx means area under the curve y at the base x. That means you should know what is x, here it is moles. What is y? 1 by minus Ra into V. You should know these two things to plot the graph. One is y axis, one is x axis. What is the y axis? 1 by minus Ra into V is my y axis, Na, that means moles, is on x axis. Finally, if you plot a graph, area under the curve will give you time, because time is nothing but integral y dx. So, these are my experimental data. That means I have conducted few experiments, and what I done is I have taken some samples with a random time interval. Okay, first I have taken out some sample. Okay, I have measured how many moles of A is left. After some point of time, I did not fix the time. After some point of time, again I have taken out the sample from the reactor. I have measured how many number of moles still left. So, I know the moles. Example, when moles is 4, the speed or rate of reaction is 0.2 mole per liter per minute. That means you can easily measure the rate. Once you know the moles, you know the initial moles minus final initial moles. I mean, like that, if you do some mathematics, you can able to find out the speed at which the reaction is happening between the two time intervals. Imagine you have these two data. One is moles, what is the moles in the reactor at that time, what is the speed of the reaction. 4, my speed is 0.2. When the moles are 2.42, my speed is 1.21. Like that, more is the moles, more is the speed. less is the moles, less is the speed. As the reaction is progressing, the moles of A is getting reduced, so that the rate of reaction has got reduced. These two are my experimental data. What I need to plot is 1 by minus Ra into V on y axis, moles is on x axis. So, I know Ra minus Ra, I know the 2 liter reactor is here, minus Ra into 2, that means 0.2 into 2 is equal to 0.4, 0.121 into 2 is equal to 0.242, like that 0.009 into 2 is equal to 0.018. Now, you know minus Ra into V, 1 by minus Ra into V is 1 by 0.4, 1 by 2.42, 0.242, like that. If you do, you get what you need is on x axis you need have moles, on the y axis you need to have minus 1 by minus Ra into V. So, therefore, I got the data, I have plotted. Okay. Now, you can able to find out time, what time before the start of the reaction my moles is 4 moles. I want to know, to reduce the moles from 4 to 0.54, how much time is required. That means on the graph you need to locate these 2 points, one is 4 and the second is 0.54. Okay. And now you mark this and find the area under the curve between these 2 points and you get the time, because area under the curve nothing but the time. Now, from Excel, we have found out, that means you can plot the data, fit a power line, find out the area under the curve, or manually plot the graph and count a number of squares or area under the curve. Finally, you will get 20. That means 20 minutes. This is how people normally go with this kind of graphical solution, provided if you know the moles and if you know the rate. Similarly, here we went through the moles, here we went through the concentration. Okay, same way, time is nothing but Ca to Ca0 dCa by minus Ra. That means integral Ca to Ca0 minus 1 by Ra, 1 by minus Ra into dCa. Here you can again integral y into dx. Okay. What is y here? 1 by minus Ra is y. What is x here? It is nothing but concentration. That means you need to plot on y axis 1 by minus Ra, on the x axis concentration. If you plot, here from the experiments, that means here I have measured moles and here I have measured the concentration. From the concentration I can able to measure the speed of a reaction. Imagine you have this data, that means I have at random time I have removed some sample, I have measured how much amount of concentration is A and have measured what is the rate of reaction at that particular concentration. So, I have at 2 mole per liter, I have 0.2 mole per liter per minute speed or rate of reaction. Like that, I have measured different samples, I have taken out different samples from the reactor and I have measured the concentration, I have measured the speed of the reaction. Here see, more is the concentration, more is the speed, less is the concentration, less is the speed, normally typically observed for this empirical elementary reactions. I know, but what I need is on y axis 1 by minus Ra. If I know Ra, I know 1 by minus Ra. Now I have plotted minus 1 by Ra on y axis, concentration on x axis, because I have both the data with me. Now you have got the plot, you know the curve, fit a curve, draw a curve connecting all the dots, all the data points. Now you have to find a time. What time? I have started with a concentration of 2 mole per liter in the reactor, that means initial concentration. I want to find out time, that at what time my concentration of A will be reduced to 0.27 mole per liter. My starting concentration is 2 mole per liter, ending concentration is 0.27 mole per liter. To reduce the concentration from here to here, how much time is required? It is very simple. Okay. My initial concentration Ca0, final concentration is 0.27, draw the straight lines, till it meets the curve, and find the area under this curve. The area under the curve is nothing but the time, because the time is nothing but the area under this curve. Now from this you can get the it takes 20 minutes for the concentration to reach to 0.27 mole per liter from 2 mole per liter. So this is the graphical method of finding the time, provided if you know the data, experimental data is given. I hope you have learned. Let us meet up with the new reactor.